Welcome to our journey through the fascinating world of units and measurement. Imagine trying to bake a cake without measuring cups, or building a bridge without knowing lengths. Measurement is the language scientists use to describe our universe. We compare every physical quantity, like mass, length, or time, to a standard reference called a unit. Some units are basic, like meters for length, while others, like speed, are combinations of these base units. Today, we'll explore how this system evolved and why the SI system became the global standard. Let's dive into the 7 SI base units, the foundation stones of all physical measurements. These include the meter for length, kilogram for mass, second for time, ampere for electric current, Kelvin for temperature, mole for amount of substance, and candela for luminous intensity. Ever wondered why we use radians and steradians for angles? They measure plane and solid angles, and are dimensionless. Thanks to SI's decimal system, conversions are a breeze. This structure makes scientific communication universal and precise. While SI units reign supreme in science, some familiar units still stick around. Think minutes, hours, days, or even liters and tons. The table here shows their SI equivalents. Now, let's talk about significant figures. These tell us how precise our measurements are. For example, measuring a pendulum's period as 1.62 seconds means we're confident about the first 2 digits and a bit uncertain about the last one. No matter which units you choose, the number of significant figures remains unchanged. How do you know which digits truly matter in a measurement? That's where rules for significant figures come in. All non-zero digits count, zeros sandwiched between them count too, but leading zeros don't. Trailing zeros only count if there's a decimal point. To avoid confusion, especially with lots of zeros, scientists use scientific notation. For instance, Earth's diameter is about 1.28 times 10 meters. Here, every digit in the main number is significant. This clarity ensures everyone interprets data the same way. Let's tackle arithmetic with significant figures. When multiplying or dividing measurements, your answer can't be more precise than your least precise value, so always match the smallest number of significant figures. For addition or subtraction, it's about matching decimal places instead. Imagine calculating density. If mass is 4.237 g, for sig figs, and volume is 2.51 cubic centimeters, 3 sig figs, density should be rounded to 3 significant figures, 1.69 g/cm superscript 3. Rounding conventions help us avoid false precision and keep results trustworthy. Let's see these rules in action. Suppose each side of a cube measures 7.203 meters. Since that's 4 significant figures, both surface area and volume should be rounded accordingly, 311.3 square meters and 373.7 cubic meters. Or consider finding density. If you have 5.74 g and 1.2 cubic centimeters, express the result to 2 significant figures, 4.8 g/cm superscript 3. Remember, uncertainty is part of every measurement. By tracking significant figures and errors properly, scientists ensure their results are both honest and meaningful. Let's dive into the fascinating world of dimensions in physics. Every physical quantity, like length, mass, or time, can be described using 7 fundamental dimensions, each represented with square brackets. For example, volume is simply L superscript 3, and force becomes mLT superscript 2. Why is this useful? It allows us to express complex quantities using just a few building blocks. Dimensional formulae show how base quantities combine, while dimensional equations equate a quantity to its dimensional formula, making relationships between concepts much clearer. This approach helps prevent calculation errors and keeps our physics precise. Dimensional analysis isn't just theory, it's a powerful tool for checking if equations make sense. The rule? Only quantities with the same dimensions can be added or subtracted. Take the classic equation for distance x equals x plus vt plus 1/2 at superscript 2. Each term must have the dimension of length, L, to be valid. If even one term doesn't match, the whole equation is incorrect. While dimensional consistency doesn't guarantee an equation is right, it quickly reveals if something's definitely wrong, saving you from major mistakes before you even start calculating. Let's put dimensional analysis to work with real examples. For kinetic energy formulas, only those matching the dimensions mL superscript 2 T superscript 2 are valid. Some options look right but fail this test, so dimensional analysis helps us rule out mistakes fast. Now, what about deducing relationships? Consider a simple pendulum. By expressing its time period as a combination of length and gravity, we use dimensions to arrive at T equals K times the square root of L over G. Notice how we can't find the exact constant K, just the form of the relationship. Let's recap the essentials. Physics builds on measurement, using 7 base quantities and their standardized units, like meter, kilogram, and second. We use scientific notation to handle huge or tiny numbers with ease. SI units keep things consistent across the globe, and derived units like Joule and Newton spring from these basics. Dimensional analysis checks if our equations make sense, while significant figures ensure our calculations stay accurate. Ready to test your skills? Try converting units or filling in the blanks. Practice is key to mastering these concepts. Let's tackle some thought-provoking problems. Imagine converting calories to joules or redefining what large means by comparing to clear standards. Suddenly, size isn't so absolute. Which tool measures length most precisely, a vernier caliper, screw gauge, or optical instrument? And when measuring something tiny, like a human hair's thickness under a microscope, why do more measurements lead to better accuracy? Don't forget significant figures. They're vital for reliable results in every calculation you make. Let's wrap up with some mind-expanding questions. How tiny is an atom in meters? Why does a mole of gas occupy so much more space than a mole of atoms? When riding a fast train, why do nearby trees whiz by while distant hills barely seem to move? And what makes the sun so unique in terms of mass and density? These questions invite you to connect measurement concepts with real-world phenomena, fueling your curiosity and deepening your understanding of physics.